So far, we have discussed the system that consists of a single object. We found that work done by an external force from the environment is equal to the change of kinetic energy. Now, we will look at the system of many objects with the interaction among its members. For example, consider the Earth book system as in this figure. In this system, we have the book here and the Earth as a member of the system. Our applied force is the interaction between the environment to the system. Okay, and we are interested in the effect that the applied force from the environment will have on the especially the energy of the system. Okay, since the Earth is so massive, we will consider the motion of the book only. So, we will look at the kinetic energy of the book only. If we leave the book initially at rest, maybe here, initially at rest here, and leave it to this point and also at rest at the final position. So there is no change in the kinetic energy because the speed of the book here is 0 and the speed of the book here is 0. So we have that the change of the kinetic energy is 0. If we do a quasi-static or quasi-equilibrium process, quasi-static or quasi-equilibrium, that is, we lift the book very slowly. We lift this book very slowly. The external force applied to the book is approximately equal in magnitude with the gravity. Because the book moves very slowly, we can assume that these two forces are equal in magnitude, but they have opposite direction. Okay, so we have that the applied force is approximately equal in magnitude with the gravitational force, but in opposite direction. Here we define the upward direction as a positive direction of the y-axis. Okay, so the unit vector j point upward like this. And because of this relation, we will have that the work done by the applied force is equal to W from the external applied force is equal to the mg by f minus mg yi In this case, we lift the book vertically, okay, like this. But it is easy to show that this is not depend on how we lift the book. We may lift the book in this part. And if we lift it very slowly, that is, it is a quasi-equilibrium or the quasi-static process. That is, the applied force is approximately equal in magnitude with the gravitational force, but has the opposite direction. We will have this relation. This is quite simple. For example, if you lift an object in this part, okay, but you can see that this is a gravitational force. So if you do it in the quasi-static process, it means that all the time your external force or applied force will point in this direction. So the work done is F R cos theta, which equal to F Y. This is the angle theta. Okay, and R cos theta, this is Y, which equal to R cos theta. Okay, this is R. So you can see that even we lift the object not vertically but in this direction, the net work is equal to the mgy. Okay, so this relation is correct in general. In this situation, we do some work to the system, right? This is the work done that the external force do to the system, but the book is at rest at the initial point. It is at rest at the final point. So there is no change in the kinetic energy. It means that the work kinetic energy is not applied here. We perform some work on the system, but there is no change in kinetic energy. However, if we release the book, okay, if we put the book here and after that we release the book, we know for certain that the book will drop down. Okay, and we gain the kinetic energy if we release the book from this position. Lifting the book against the gravity is like we supply some kind of energy to the system. This energy will transform. When we release the book, it will transform to the kinetic energy. We call what we supply to the system by lifting the book against the gravity as the potential energy. By definition, the gravitational potential energy is defined as follows. gravitational potential energy. That is, if we have an object which is at the vertical position y above some reference point, we say that the potential energy Ug is equal to mgy. Okay, so from this definition we can see that work done by the external force is equal to the delta Ug, which is equal to the mgyf minus mgyi. It is important to see that from the definition of the gravitational potential energy here, Ug is equal to mgy, the value of the potential energy is depend on the reference point. In this figure, we use this point as the reference point and we measure the vertical position of the object from this reference point. But we are free to choose the reference point. So it means that if we change the reference point to be the new one here, I may call it the reference 2, and the vertical position of the object is y2, you can see that the value of the potential energy change if you change the reference point. So when you talk about the potential energy, you have to specify the reference point. Where is your reference point? Anyway, even the gravitational potential energy depends on the choice of the reference point. The change in the gravitational potential is not depend on the choice of the reference point. Okay, you can see that if the object move, if you have an object and it moves from the initial to final point like this, it's not depend on the reference point. You may choose this as the reference 1 and you have this is yi1 and this is yf1, and you may choose the different reference point. For example, this is the reference, this is a reference point 2, and you have this is a yi2 and this is a yf2.